picture walking through ancient Rome, turning a bronze dolphin's spout at a public fountain, and watching crystal-clear mountain water flow out, water that travelled through miles of lead pipes yet remained safe to drink, while modern Flint, Michigan's water, became toxic after just months in similar pipes. So sit back, grab a cup of tea, and get ready to discover the surprising truth about Roman lead pipes and why they didn't poison the empire, explore how water chemistry and mineral deposits created natural protection, uncover the myth-busting science that challenges everything you've heard about lead plumbing in ancient Rome, and learn what Roman engineering can teach us about infrastructure that modern assumptions completely miss. For centuries, historians have pointed to lead pipes as a prime suspect in Rome's decline. The theory seemed obvious. Romans used lead pipes extensively. Lead is toxic. Therefore, Romans must have suffered from widespread lead poisoning that contributed to the empire's fall. This narrative appears in countless textbooks, documentaries, and popular histories. There's just one problem. It's almost certainly wrong. Recent scientific analysis of Roman water systems reveals a fascinating truth that overturns this long-held belief. The lead pipes that carried water throughout the Roman Empire were often safer than the lead pipes used in American cities well into the 20th century. The secret lay not in the pipes themselves, but in the water flowing through them. Roman engineers, through a combination of deliberate design and fortunate geography, created conditions where their lead pipes developed protective mineral coatings that prevented lead from leaching into the water supply. The story begins with understanding what Roman lead pipes, called fistulae, actually were. These weren't crude tubes hammered together by ancient metalworkers, but sophisticated products of a highly developed industry. Roman plumbers, and yes, the word plumber comes from the Latin plumbum, meaning lead, manufactured pipes to standardized sizes across the empire. A fistula found in Britain would match specifications of one made in Syria, demonstrating remarkable industrial standardization 2,000 years before ISO standards. Manufacturing these pipes required considerable skill. Workers would cast lead sheets of uniform thickness, then bend them around wooden forms to create tubes. The seam where edges met was soldered with molten lead, creating a watertight seal. Skilled craftsmen could produce pipes ranging from tiny half-inch diameter tubes for household use to massive conduits over a foot across for main distribution lines. The largest pipes discovered weigh several hundred pounds per section, testament to Roman ambitions in water distribution. But why use lead at all? Romans had alternatives. They made pipes from terracotta, wood, and even bronze. The choice of lead wasn't ignorance but pragmatism. Lead is remarkably easy to work with. It melts at relatively low temperatures, making it simple to cast and solder. It's malleable enough to bend around corners without breaking, yet strong enough to withstand water pressure. Lead resists corrosion in most conditions and can last centuries buried underground. For a civilization building continental-scale water infrastructure, lead offered the best combination of workability, durability, and availability. Romans weren't unaware of lead's potential dangers. Ancient physicians like Galen wrote about lead poisoning among workers in lead mines and smelters. Vitruvius, the Roman architect and engineer, specifically noted that water carried in lead pipes could be harmful and recommended terracotta pipes when possible. Yet despite this knowledge, Romans continued using lead pipes throughout their empire. This wasn't carelessness. They had discovered something about water chemistry that we're only now fully understanding. The key to Roman water safety lay in their water sources. Roman aqueducts primarily drew from springs in limestone regions, the Apennine Mountains for Rome itself, similar geological formations throughout the empire. This limestone-filtered water was naturally hard, containing high levels of dissolved calcium and carbonate ions. When this hard water flowed through lead pipes, chemistry took over in ways that protected Roman health. As calcium-rich water flows through pipes, it deposits calcium carbonate, the same mineral that forms stalactites in caves. In Roman lead pipes, this process created a protective scale layer on the pipe's interior surface. This scale, sometimes several millimeters thick, formed a barrier between the lead pipe walls and the flowing water. It's like the pipe developed its own internal protective coating, preventing lead from dissolving into the water supply. Modern analysis of excavated Roman pipes confirms this protective mechanism. Scientists have found thick calcium carbonate deposits lining pipes throughout the former empire. Chemical analysis shows these deposits are nearly pure calcium carbonate with minimal lead content. The water flowing through these scaled pipes would have contacted limestone, not lead. It's as if the Romans were actually drinking water from stone pipes that happened to have lead structural support. The formation of this protective scale wasn't accidental, but resulted from several factors in Roman water system design. First, the continuous flow of water through Roman pipes promoted scale formation. Unlike modern systems where water can sit stagnant in pipes, Roman aqueducts delivered water in constant motion. This continuous flow brought fresh calcium carbonate to deposit on pipe walls, while preventing the acidic conditions that can develop in standing water and dissolve protective scale. Roman fountains played a crucial role in maintaining water quality. These weren't merely decorative features, but functional components of the water system. Rome had hundreds of public fountains running continuously, day and night. This constant flow served multiple purposes. It prevented water stagnation, maintained positive pressure throughout the system, and provided overflow outlets that kept the entire network in motion. The sight and sound of ever-flowing fountains became so associated with Roman civilization that their silence marked societal collapse. The overflow system deserves special attention. Roman engineers designed their water distribution with built-in waste. Fountains overflowed into drainage channels, baths constantly refreshed their water, and public latrines used running water for waste removal. This apparent profligacy actually protected public health. Moving water can't stagnate and develop the acidic conditions that dissolve protective scale and leach lead. What seems like waste was actually a sophisticated public health measure. Water temperature also influenced lead safety. Roman aqueducts carried cool spring water that remained relatively cold even in summer thanks to underground channels and covered conduits. Cold water dissolves less lead than hot water and promotes better scale formation. Romans did heat water for baths, but typically in bronze or lead-lined concrete vessels, rather than within the pipes themselves. By the time heated bath water contacted lead fixtures, it had already picked up additional minerals that reduced its ability to dissolve lead. Seasonal variations in water chemistry provided additional protection. Spring snowmelt might temporarily soften water, but Roman systems' enormous volume buffered these changes. Multiple aqueducts feeding cities meant water mixed from various sources, averaging out chemical variations. Storage reservoirs and distribution tanks allowed particulates to settle and water chemistry to stabilize before reaching consumers. These features, designed for reliable supply, incidentally protected water quality. But what about lead exposure from other sources? This is where examining the lead-poisoned Rome hypothesis becomes really interesting. Romans did face lead exposure beyond water pipes, from cosmetics, food preparation, and especially wine. Wealthy Romans often added lead acetate, called sapa, to wine as a sweetener and preservative. They cooked acidic foods in lead-glazed pottery. They used lead-based face powders and rouge. If we find evidence of lead exposure in Roman remains, these sources are far more likely culprits than water pipes. Modern bioarchaeological studies, analysing lead levels in ancient Roman skeletons, provide crucial evidence. While some Romans did show elevated lead levels, the patterns don't match what we'd expect from water-based poisoning. Lead exposure varied dramatically by social class, gender, and occupation. Wealthy Romans often showed higher lead levels than poor ones, opposite of what universal water contamination would cause. Women who used lead cosmetics sometimes showed higher levels than men. Plumbers and metalworkers showed occupational exposure. These patterns point to lifestyle and occupational exposure, not contaminated water supplies. The most telling evidence comes from comparing Roman skeletons from different regions. If lead water pipes caused widespread poisoning, we'd expect to see elevated lead levels throughout the empire wherever such pipes were used. Instead, lead levels vary by local customs, available trade goods, and economic status. Romans living in areas without lead pipes sometimes showed higher lead exposure than those in cities with extensive lead plumbing. The pipes weren't the primary problem. Let's examine specific Roman cities to understand how their water systems functioned. Rome itself had 11 major aqueducts by the height of the empire, delivering an estimated 300 million gallons daily to a population of 1 million. This works out to 300 gallons per person per day, far exceeding modern urban water consumption. The Aqua Claudia and Anio Novus, two of the largest aqueducts, brought water from sources 40 miles away, maintaining gentle gradients that kept water flowing without excessive pressure that might damage pipes. Pompeii offers unique insights, because Vesuvius preserved its water system in working condition. Archaeologists have traced the entire network from the aqueduct arrival point through distribution tanks to individual homes and fountains. Lead pipes are everywhere, yet analysis of human remains from Pompeii shows lead levels no higher than contemporary populations elsewhere. The pipes retained thick calcium deposits, and the system's design ensured constant flow. Even the catastrophic earthquake 17 years before the eruption, which damaged many pipes and required repairs, didn't create conditions for increased lead exposure. Ostia, Rome's port city, presents another case study. As a commercial hub, Ostia had extensive lead plumbing serving warehouses, baths, and apartment buildings. The city's proximity to the sea meant some saltwater intrusion, yet the lead pipes show protective scaling similar to inland cities. Marine minerals added complexity to the scale chemistry, but didn't prevent protective coating formation. Ostian skeletons show lead exposure patterns consistent with occupation and lifestyle, not water contamination. Provincial cities across the empire replicated Roman water management principles with local adaptations. Nimes in Gaul, Segovia in Spain, and Carthage in Africa all built aqueduct systems following Roman models, each adapted to local water chemistry, harder or softer water, different mineral content, yet the basic principle of continuous flow through lead pipes remained consistent. Archaeological evidence from these diverse locations shows similar protective scaling in pipes, and no evidence of widespread lead poisoning from water supplies. The engineering specifics of Roman water distribution reveal sophisticated understanding of hydraulic principles. Distribution tanks, called castella, served as pressure breakpoints and flow dividers. Water arrived at these tanks through aqueducts, then split into multiple lead pipes serving different districts. The tank's design, with inlet pipes set higher than outlets, created natural overflow protection. If demand dropped, excess water overflowed harmlessly rather than building dangerous pressure in the pipes. Pipe standardization went beyond mere convenience. Romans designated pipes by their internal cross-sectional area in square digits, a digit being roughly 3/4 inch. A quinaria pipe had 5 square digits of area, a vicunaria had 20. This standardization allowed engineers to calculate flow rates, pressure drops, and system capacity with remarkable precision. Contracts for water supply specified pipe sizes, ensuring customers received their paid allocation. Tampering with pipe sizes was a serious crime punished by heavy fines. The joining methods for lead pipes showed similar sophistication. Simple soldering worked for low-pressure applications, but main distribution lines required stronger connections. Roman plumbers developed various joint types: sleeve joints where one pipe fit inside another, flange joints for accessing maintenance points, and specialized fittings for corners and branches. They understood that joints were weak points and often wrapped them with iron bands for reinforcement. Some joints included primitive gaskets made from leather or cloth soaked in pitch. Pressure management in Roman systems prevented many problems that plague modern plumbing. Rather than using high pressure to force water uphill, Romans relied on gravity flow from elevated sources. Where they needed to cross valleys, they built siphons, inverse U-shaped pipe systems that used water's weight to push it up the far side. These siphons required careful engineering to prevent airlocks and manage pressure, but they avoided the extreme pressures that can damage pipes and joints. Maintenance of Roman water systems required organized effort. Cities employed teams of aquarii, water workers, who patrolled aqueducts, cleaned settling tanks, repaired leaks, and managed distribution. Frontinus, who served as Rome's water commissioner around 100 CE, wrote extensively about his management challenges. He complained about illegal taps, oversized pipes, and unauthorized connections. His solutions included regular inspections, harsh penalties for water theft, and a comprehensive survey of the entire system. His written work, De Aquaeductu, provides invaluable insights into Roman water management. The social and economic factors surrounding Roman water distribution reveal a complex system balancing public good with private profit. Water was considered a public right, hence the free-flowing public fountains accessible to all, but private connections to homes, baths, and businesses required payment. Wealthy Romans paid substantial fees for private water supplies, funding system maintenance, and expansion. This two-tier system ensured basic water access for all while generating revenue for infrastructure. The fountain culture of Rome deserves special consideration. Public fountains weren't just water sources, but social centres. People gathered to collect water, exchange news, conduct business, and socialise. Fountain placement followed careful planning. No Roman was supposed to walk more than 500 feet to reach public water. Decorative elements, sculptures, inscriptions, architectural frames turned functional infrastructure into urban art. The sound of flowing water became Rome's soundtrack, a constant reminder of engineering prowess and urban amenity. Bathhouses represented the largest single use of Roman water infrastructure. A major bath complex like the baths of Caracalla used millions of gallons daily. Water flowed through the facility in a carefully planned sequence, first filling cold pools, then warm baths, finally hot baths before draining away. This flow pattern maximised heat recovery and water use efficiency. Lead pipes carried water throughout these complexes, yet bathhouses operated for centuries without poisoning their patrons. Alternative water sources provided important supplements to aqueduct supplies. Many Romans maintained private wells and cisterns, especially in areas distant from aqueduct service. Cistern water, collected from rainfall and stored in sealed tanks, had different chemistry than aqueduct water, often softer with less protective calcium carbonate. Romans recognized this difference, often preferring cistern water for washing, because it lathered soap better, while drinking aqueduct water for its perceived health benefits. The comparison between different pipe materials illuminates Roman choices. Terracotta pipes made from fired clay cost less than lead and posed no toxicity risk, but clay pipes broke easily, especially when ground shifted or froze. Joining clay pipes reliably was difficult. Leaks at every joint wasted precious water. Wooden pipes rotted unless made from expensive, rot-resistant species. Bronze pipes cost far more than lead and were reserved for special applications. For a practical empire building continental infrastructure, lead provided the best balance of cost, durability, and workability. Elite Romans sometimes chose alternative materials for aesthetic or health reasons. Archaeological excavations of luxury villas have found bronze fixtures and marble-lined channels. The villa of the Papyri at Herculaneum featured an elaborate water system with bronze pipes and taps, demonstrating that wealthy Romans could avoid lead if they chose. Yet even in these elite settings, lead pipes often handled the basic plumbing, with precious metals reserved for visible fixtures. Modern parallels illuminate both Roman successes and our own failures. The Flint water crisis provides a particularly instructive comparison. Flint's pipes, like Roman ones, had developed protective scale over decades of use. When the city switched water sources to save money, the new water's chemistry was more acidic and lacked the minerals that maintained the protective coating. The scale dissolved, exposing bare lead to corrosive water. Lead levels skyrocketed, poisoning thousands. Romans avoided this catastrophe by maintaining consistent water sources and chemistry. Washington, D.C.'s lead crisis of the early 2000s offers another parallel. The city switched from chlorine to chloramine for water disinfection, inadvertently changing water chemistry in ways that dissolved protective pipe scale. Lead levels spiked until the city adjusted its water treatment. Romans lacked our chemical options, but achieved similar results through system design. Continuous flow and consistent sourcing, maintained stable chemistry without chemical intervention. The scientific evidence from modern studies of Roman pipes continues to accumulate. Isotope analysis can now determine not just lead levels but lead sources. Different lead ores have distinct isotopic signatures, allowing researchers to trace whether lead in bones came from pipes, cosmetics, or food contamination. Studies consistently show that skeletal lead doesn't match local pipe lead isotopically, further evidence that pipes weren't the primary exposure source. Microscopic analysis of pipe scale reveals complex layered structures built up over centuries. The oldest layers, closest to the pipe wall, often show initial corrosion as pipes equilibrated with water chemistry, but subsequent layers are nearly pure calcium carbonate, sometimes interspersed with other minerals depending on local water composition. These scales were remarkably stable. Many survived intact through 2 millennia of burial, testament to their chemical durability. Public health lessons from Roman water systems remain relevant today. Many American cities still have extensive lead pipe infrastructure, a problem highlighted by Flint but widespread nationwide. The solution isn't necessarily pipe replacement, a costly and disruptive process, but managing water chemistry to maintain protective scale. Regular monitoring, consistent treatment, and avoiding sudden changes can keep old lead pipes safe. Romans achieved this through system design. We can achieve it through careful management. The myth of lead-poisoned Rome tells us as much about modern assumptions as ancient realities. We often assume technological progress is linear, that older must mean more primitive and dangerous. Roman water systems challenge this assumption. In some ways, their continuous flow gravity-fed systems were more elegant and sustainable than our energy-intensive, chemical-dependent modern systems. They achieved safe water through design rather than intervention. Environmental considerations add another dimension to Roman water management. Their systems required no external power beyond gravity. No pumps consuming electricity, no treatment plants using chemicals, no complex automation requiring constant maintenance. Water flowed from mountain springs to city fountains through entirely passive infrastructure. The environmental footprint was limited to initial construction. Modern systems, for all their sophistication, require continuous energy and chemical inputs. The social equity of Roman water distribution also deserves recognition. While wealthy Romans enjoyed private supplies, the public fountain system ensured everyone had access to clean water. This wasn't charity, but pragmatic public health policy. Diseases spread regardless of social class, ensuring clean water for all protected everyone. Modern cities sometimes forget this lesson, allowing water infrastructure in poor neighborhoods to deteriorate while maintaining premium service in wealthy areas. Archaeological discoveries continue to refine our understanding of Roman water systems. Recent excavations have uncovered previously unknown aqueduct branches, distribution networks in provincial towns, and evidence of system modifications over time. Each discovery adds detail to our picture of Roman hydraulic engineering. Advanced technologies like ground-penetrating radar and satellite imagery reveal buried infrastructure, mapping networks more extensive than previously imagined. Climate data extracted from Roman pipe scale provides unexpected bonuses for researchers. The chemical composition of calcium carbonate deposits records information about ancient water sources, temperatures, and even rainfall patterns. Annual layers in thick scale deposits create timelines of environmental conditions. Roman water infrastructure thus serves as an inadvertent climate archive, preserving data about the Mediterranean environment 2,000 years ago. The question of why this knowledge was lost deserves consideration. Medieval Europeans inherited Roman aqueducts and pipes, but not the understanding of water chemistry that made them safe. As aqueducts fell into disrepair, cities reverted to wells and cisterns. Lead pipes were sometimes salvaged for their metal value. The continuous flow that protected Roman water quality ceased. When Renaissance engineers tried to restore ancient systems, they focused on hydraulic engineering while missing crucial chemical factors. Modern materials, science has finally caught up to understanding what Romans achieved through experience. We now know precisely why calcium carbonate scale forms, how water chemistry affects lead solubility, and what conditions promote or prevent protective coating formation. This knowledge validates Roman practices while informing modern water treatment. Sometimes ancient wisdom awaits only proper scientific framework for explanation. The legacy of Roman water systems extends beyond technical achievements. Romans demonstrated that urban populations could have abundant, clean water through public investment in infrastructure. They showed that standardization and systematic management could deliver services efficiently across vast territories. They proved that environmental constraints, like gravity-fed systems, could inspire elegant engineering solutions. These lessons apply whether building with lead pipes or modern materials. As we face our own infrastructure challenges, aging pipes, limited budgets, environmental concerns, Roman examples offer both inspiration and practical guidance. Their emphasis on continuous flow and overflow protection could reduce water age in modern systems. Their use of local materials and passive flow could decrease energy consumption. Their commitment to public access could guide equitable water policy. Ancient solutions needn't be adopted wholesale but can inform modern approaches. The story of Roman lead pipes ultimately isn't about lead at all. It's about water chemistry, system design, and public health engineering. Romans succeeded not by avoiding lead, but by understanding how to use it safely. They created conditions where a potentially dangerous material became safe through careful management. This nuanced reality replaces the simplistic narrative of ancient ignorance with appreciation for sophisticated engineering. As you finish your tea and reflect on this journey through Roman water systems, consider how completely the evidence overturns popular assumptions. The lead pipes that supposedly doomed Rome actually demonstrate remarkable public health engineering. The wasteful overflow fountains actually protected water quality. The primitive gravity-fed systems actually surpassed modern pressurized networks in some ways. Roman engineers, working without modern chemistry or material science, achieved safe water through careful observation and systematic design. The next time you see water flowing from a tap, consider the complex systems making that simple act possible. Romans faced the same challenge, delivering clean water safely to urban populations, and solved it with remarkable elegance. Their lead pipes, properly understood, weren't a sign of ancient ignorance but of engineering sophistication. They remind us that good engineering considers not just materials, but how those materials interact with their environment over time. In the end, the myth of lead-poisoned Rome reveals more about modern prejudices than ancient practices. We want simple explanations for complex historical events. The fall of a great empire must have a great cause. Surely widespread poisoning would suffice. But history resists such simplification. Rome fell for countless reasons over centuries, but lead pipes weren't among them. The water that flowed through those pipes sustained one of history's greatest civilizations, and understanding how they achieved this feat makes their accomplishment all the more remarkable. Today's engineers and policymakers could learn much from Roman water management. Not to copy their methods directly, we have better materials and deeper scientific understanding, but to emulate their systematic approach, their commitment to public access, and their patience in developing solutions through observation and experience. The Roman water system stands as proof that sustainable, equitable urban infrastructure is possible. We need only the wisdom to build it and the commitment to maintain it. The truth about Roman lead pipes, that they were safe because of protective mineral coatings formed by water chemistry, transforms a supposed ancient failure into an engineering triumph. It replaces a cautionary tale about ignorance with an inspiring example of practical problem-solving. Most importantly, it reminds us to question accepted wisdom, examine evidence carefully, and appreciate the sophistication of past societies. Romans weren't poisoned by their pipes. They were sustained by water systems that we're only now learning to fully appreciate.